2. Now right away I noticed that if this were the single elementary reaction, we would be proposing a termolecular elementary step. We realize that 3 molecules colliding in space with just the right orientation, with just the right energy, is not going to happen. Therefore, I know that this observed rate law is coming from what we would call a fast initial step. And what we're doing now is relating an intermediate in terms of an initial reactant. How could this happen, it asked. Let's predict a reaction mechanism for this rate law. What we have are 2 molecules of NO2 and a single molecule of Br2. Do we believe that a single molecule, let's just try to get those where I have 2 NOs. Perhaps this could be an NO, and I'll get this one off. This could be another molecule of NO, and then here would be the molecule of Br2. Okay, so I don't really need all these extra bonds. Alrighty, so 2 molecules of NO and a molecule of Br2. We have to propose a mechanism to get these to our product side, 2 molecules of NOBr. We have to decide, first of all, that we agree that all 3 aren't going to collide with just the right orientation to go directly to product. A 3-molecule collision is not likely. So, a couple of things. Do we want to propose, as in this first step, one possibility is that an NO-NO-Br2, all 3 collide, bam, and then we say not likely. That termolecular equation is not a likely choice. So I'll just record that. Termolecular is not likely. So we're eliminating that choice. NO plus Br2 will not be an elementary step. So again, if we just flip the page of our notes, let's propose a second alternative mechanism. Instead of one step where all 3 collide, what might be a different pathway? A couple of options to consider. Suppose I take an NO and a Br and collide that. Or the other choice would be take the 2 like molecules and collide that. It really doesn't matter what you propose because we'll make an intermediate and then use it up in the next step. So we've got 3 molecules. Let's propose in a first collision that I take a molecule of NO and collide it with a molecule of Br2. In an NO and a Br2 collide, that's a bimolecular elementary reaction that's very likely. So I'm all right here. And yet I know that I need to produce an intermediate. If NO and Br2 collide, let's just put them together and get an NO-Br2. All right, so we'll have a molecule form where they're all connected together. And again, that mechanism that I'm proposing is not the observed rate law, so I know it cannot be the slowest step. It must be a fast step. Just thinking that through, it's the next step that's going to have a larger activation energy. Because see, if the observed rate law was NO to the first order and Br2 to the first order, then I know the observed rate law would come from that slowest first step. But it's not telling me that. The rate law was second order with respect to NO and first order with respect to bromine. This is not the observed rate law, so this cannot be the slow step. It must be the faster of the 2 steps with a lower activation energy. So now I have this product, this first product, NOBr2. That's not appearing in the overall equation, so I know that it needs to be used up. It needs to be an intermediate. We have that second molecule of NO that needs to collide as well. In my next collision, of my proposed mechanism, I'll take that unused NOBr2 produced here and now use it up here, collide it with that unused NO molecule from the original 3 molecules, and go on to form 2 units of NOBr2, NOBr. Remember the overall equation we were trying to form just from the previous page? 2 NOs plus Br2 give us 2 units of NOBr. I made an intermediate, used it up immediately. I proposed a mechanism that had a slow second step. Now, if this is the rate determining step, which it is, it has the highest activation energy, here's what we're now determining. That the overall equation comes, the overall rate law comes from the slowest step. This is what it would look like. Rate is equal to K times the concentration of NOBr2 times the concentration of NO, both first order. This would be a bimolecular elementary reaction. The problem is we are not allowed to have an intermediate in our equation. It's too difficult to measure concentrations of intermediates. I mean, because as soon as they're made, they get consumed. How are we going to measure the molarity of something like that? So the NOBr2 is an intermediate, and we're not allowed to express rate laws with an intermediate. But no big deal. What we'll go back to do is talk about the elementary reactions above. Knowing that K1, this rate law from that first elementary reaction, and K2 come from those elementary reactions, here's what we're just thinking this through. If I have a fast first step, NO plus Br2 are going to collide very quickly and produce NOBr2. This starts to accumulate faster than it can get used. And when it starts to accumulate, just like a bottleneck, I'm making step 1 goes fast, 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 but it's got nowhere to go, and eventually this concentration begins to rise. What then happens is an equilibrium is established. NOBr2 will go back to the original product. And what happens is we call that a K-1, the equilibrium of our first elementary reaction. So in the fast first step, when we start to accumulate product faster than it can get consumed in the next reaction, we make that assumption that an equilibrium is forming. And with that equilibrium happening, it just reads for us, step 1, both forward and reverse are occurring very rapidly with respect to step 2. We begin to create what's known as a dynamic equilibrium. Their rates are equal. So just thinking that through, K1, the forward reaction, would have a rate law that looks like NO, parenthesis, BR, parenthesis, both first order. So rate is equal to K times the concentration of NO, first order, and Br2, first order. This is the forward direction. And since their rates are equal, I'll set that equal to K-1, the opposite direction. And now what we have is NOBr2, again, first order with respect to the reverse reaction. So I'm simply looking at it from right to left. The forward reaction has its own rate law. Rate is equal to K times NO with respect as first order as well as Br2. In dynamic equilibrium, the forward and reverse reaction are occurring at the same rate. We have that set equal to the reverse reaction's rate law, K-1 NOBr2. So we've set the rate of the forward reaction equal to the rate of the reverse reaction. Remember this, what our ultimate goal is to express this rate law, NOBr2, that intermediate. We want to sub in an initial reactant. What is NOBr2 equivalent to, so I can sub it out in terms of an initial reactant?